All right, I'm going to uh, take not that long, maybe just 15 or 20 minutes. At least that's my hope, to go over some of some other details about collisions and the conservation of momentum. Also, I'd like to demonstrate a full calculation that's not necessarily experimental, even though I have the experimental videos here. I'm actually just going to have those so you can just visually understand what the problem is asking. But the plan is to actually, again, use the modeling that I actually just left you guys and showed you, like how you would algebraically model conservation of momentum and collisions. So I'd like to show you one that actually applies some numerical values and actually makes a calculation. Before I do that, I wanted to point out two things that are important to know that you haven't seen yet. For one, whenever a larger mass collides with a smaller mass, a heavier object collides with a lighter object. Let's see what happens. So you'll see that this is not a surprise, that the lighter object, so this is the heavier object, by the way. This is heavier and this is lighter. I know you could tell that, but I guess it's made of metal. You can see this is longer and this is shorter. So this one's the lighter one, this is the heavier one. The point being that whenever a heavier mass collides with a stationary target, assuming that the stationary target is lighter and the moving object is the heavier one of the two, the heavy moving object will always continue moving in the same direction as it originally was after the collision. It will never bounce off the lighter object and head in the other direction. This would never hit this and head back to the left. Since it's heavier, it will maintain some momentum in the forward direction that it originally had. The lighter one, not surprisingly, gets hit and goes flying in the direction of its hit. But you need to know, again, in all cases, when a heavier object collides with a stationary means not moving, object that's lighter than the original moving object that's heavier, it'll always be the case that the heavier object maintains its original direction of motion even after the collision. It will never reverse direction. And we're referring in this case to head-on collisions, one-dimensional collisions. Okay. The opposite ends up being true when we look at the opposite scenario, which is not a larger mass colliding with a smaller mass, but instead a smaller mass colliding with a heavier mass. That's right here, small mass into large stationary mass. Let's try that one. So it's just going to be the reverse of what we just saw. That's the one that he was just using. He's now making that the stationary target. I'm guessing a little yellow goldish one's going to come from the left side. It's the lighter one. Let's see what happens. You notice that the light one reversed direction. Not surprisingly, he moves to the right because, well, he got banged. If there's enough friction under here, of course, he might not move. But this is a air track. See these little pilot holes right here? These little holes that you see here have air blowing out of them from a air compressor that's being used backwards to push air out. Actually, no, air compressors pull air in, but then ultimately push it out. But anyways, air is coming out of these holes and lifting these things up. So there's a little gap underneath them. And so it's essentially moving without friction. So with that said, any little bump, if there's truly no friction, this thing's hovering. Any bump from this thing would cause this thing to move. So it's not a surprise that it makes it move to the right. But again, the thing that I'm trying to actually bring your attention to is that the lighter one reverses direction. This is always true. This is always true. You might say, even if he was going much faster, yes. Even if he was going like really, really fast, like super duper duper fast, yes. It's a law of physics. It's necessary in order to conserve momentum as a vector quantity. Talk about that more later. But if he were to continue forward and him also would move to in the forward direction and he's lighter and he's heavier, the total momentum prior to the collision wouldn't come out as being equal to the total momentum after the collision. It would be a violation of the conservation law. Physics makes it such that those things are not violated. It's not satisfying to just say this happens because conservation laws can never be violated. I mean, there's details, there's mechanisms, right? And we get into those details and mechanisms later because I haven't told you about impulse and how forces and time of contact come into play. But once you start looking at those details, then you finally understand why this guy does and how he has to reverse direction. But we're not there yet. Just know that I'm just giving you some general information that may help you answer some multiple choice questions on an AP exam. The lighter object, regardless of its speed, if it's the one that's moving and about to collide with a heavier stationary target, the lighter object will always bounce off, or ricochet, if you want to call it that, off of the heavier object, and it will reverse direction 100% of the time. Okay. That said, let's see if we can do a problem. I'd like to actually do a problem. Well, let's do two. Let's do the. In fact, I haven't even tried this with the putty. Let's see what happens when we load this with putty. Just curious. I'm not allowed to pick putty. Oh, I see. Oop. Let's see. Nice. Okay. So this is worth talking about and showing you, because this is another inelastic collision. Inelastic because they stick, like the dart experiment you did, but the dart was way lighter than the car that it ran into. In this case, this is another one of those specific kinds of collisions that they want you to know about, which is an inelastic collision, again, yes, but between two objects that have the exact same mass. These both are identical objects. They both have the same exact amount of mass. So let's just do a quick measurement. And then I'm gonna use the modeling that I've shown you in class to make some algebraic predictions. So let's back up. Let me back this up a little bit. Back it up a little more. Let's get out a ruler and a meter stick. I'm sorry, get out a meter stick and a stopwatch. And let's measure this guy's speed. Let's do that. All right. All right. In fact, I'm going to go a little further, right up here. It's probably better. Okay. Good enough for me. So that's 1 centimeter, and it took 0.0583 seconds. So let me just do that quick distance over time calculation. 0.01, can be careful about that. It's 1 centimeter, but it has to be put in as meters because we're going to do in meters per second. 0.01 divided by 0.0583, I get 0.17. So this guy's moving at 0.17 meters per second. What did I just say? 0.17 meters per second. And I'm calling that V for velocity, A for object A. I always think of the object on the left as object A, the object on the right as object B. Textbooks do too, so just be aware. I for initial means before the collision. F for final means after the collision. What are the masses? I'm assuming it's up here. This is the large glider, 300 grams. And they're the same, right? They're both 300 grams. Mass of A is equal to mass of B, which is equal to 0.3 kg. All right, what would the momentum be for object A initially? Well, I know it's to the right, so I mean, I don't have to really necessarily worry about about the direction, at least, missing a minus sign, but I'll still put it as a vector symbol. So we have to do m, which is what, 0.3 on the calculator times 0.17, enter. I get 0.051. So by putting the plus there, and I mean, technically I'd have to put a little x to represent m along the x-axis, means it's to the right. All right. So now, how would I use only this information to make a prediction about how fast these would be moving after the collision? Let's just view it first. Does this first guy seem to slow down as a result of running into something? Well, he should. It would be a bizarre world if you run into something and you don't slow down. That would be strange. So he is slowing down, which means we know that he's losing some momentum, right, as a result of banging into this thing. But momentum is a conserved quantity. So in that case, it must have passed off that lost momentum over to the other guy. That's why the other guy starts moving. He absorbs the same amount of momentum as he loses. At least that's the theory, right? That's what we believe is the theory. It's not really a theory. I'm just saying we're learning it now, so we're trying to begin to believe it, but know that it's called a law for a reason. It's a conservation law. Law of conservation of momentum, law of conservation of energy. They're laws. They're always true. So now the question is, I obviously could measure their collective speed after the collision. I could make that measurement, but that's not the point. The point was I wanted to show again, how would you use the algebraic algebraic steps to model this and solve this. All right, so let me just write this maybe up on the top, a little smaller. VA initial is 0.17. Their masses are both 0.3. And the momentum is 0.051. All right, so this is how I would do that, right? I would say, all right, this total, again, always start just generically. Total momentum as a vector quantity has to be the same before and after the collision. Total, because I know I've got two objects. I've got to sum these up. It's a summation. So sigma is, again, a summation. So, yeah, I can write it. PA initial plus PB initial has to be equal to PA final plus PB final. All right, then this is generic at this point. Then stop and say, all right, is there anything that I can cross out? Oh, this guy was just sitting here, right? He is not moving. Object B has no momentum. He has no speed, of course. And for that reason, I can just cross out his original momentum term, which is 0, because V would have been 0. And again, these guys actually stick together and become one unit, right? For sure, right? They stick together and become one unit, moving with a mass. That's the total mass that they have. So I can really write this as, their total mass. I mean to say that their total momentum. So what does this boil down to? Well, from 4 terms to 2 terms. What is it saying? The original guy's momentum that's coming in, that's this left term. If conservation of energy is true, that total vector momentum will be equal to the total vector momentum afterwards. And again, you might say, how can that be? They're not moving at the same speed. And I'd have to remind you that the amount of moving mass is changing, right? Since momentum involves mass and speed, before the collision, you only have 150 grams of material moving. After the collision, you've got 300 grams of material in motion. So the amount of moving mass is doubling from 150 grams to 300 grams. So what do we think the speed will do? Because the product, MV, has to stay the same. right? If I continued with this, it would say MA, VA initial has to be equal to MA plus MB times V final. There's an equal sign here. It means that the total momentum here as a number has to be equal to the same number on this side in total. If the mass value is doubling from 150 to a total of 300, what does the velocity value have to do in order so that this whole side comes out equal to this whole side? Or you can think of it as, well, momentum equals m times v, v equals p over m. So what needs to happen to the velocity if the mass doubles? The momentum stays the same, right? The momentum of the moving material stays the same. Yeah, we have one block moving in the beginning and two blocks moving in the end. But in both cases, the total momentum of one block moving is the same as the total momentum of two blocks moving. This is called a constant. So if the mass is going to double, what should we expect should happen to V? Well, they're inversely proportional. We can just use our skill. M doubles. Theoretically, they should cut in half. Theoretically, their speed should be half of 0.17, about 0.085. And we can test it after to confirm, right? And we can certainly work it out. And that was the purpose of what I'm doing with you. Let's work this out. All I would do now is solve for V final, right? Just starting at this position and working my way up. V final, and again, it just, right, MA, VA initial, divided by the system's mass. And now just plug and chug. V, what is V, what is M? M was 150 grams, which is 0.15 kg. And the velocity of the original guy moving was, it's up above, 0.17, 17 centimeters per second, but we're in meters per second. I don't have to put the units. Actually, I don't usually like putting units in my calculations, just my personal preference. And then the sum of the mass is 0.3 because it's 150 plus 150, which is 300 grams, but in kilograms, that would be 0.3. What do I anticipate this should come out? It should be half of 0.17, just because theoretically that makes sense, right? If the total momentum doesn't change, the amount of moving mass doubles, then the speed has to cut in half so that the product of mass times velocity still comes out as the same number. So it still comes out as what number? This number up here. It has to still come out as 0.051. So how much momentum does this original moving guy have as he comes in? 0.051. How much momentum should they have collectively after the collision? 0.051. That's the concept, right? So let's do it. Let's do this calculation. And then I'm running out of time, so I'd have to actually make another video for the secondary type of problem I want to do with you, but that's fine. I'll do it later. I have to meet with period 8 very soon. 0.15 times 0.17 and divide by 0.3. I get 0.085. Oh, that is so exciting, right? It's half of 0.17, right? So that is the final result. 0.085 meters per second. That was their combined speed after the collision, which again is half of this. Again, but that's theoretical, but it makes sense, right? Now let's test it. Let's do a quick test because I only got a minute or two left and finish this up. So let's go back over to here and back a little bit. Bring it back a little bit. Let's go right. I mean, there's no magnets involved, so let's just go right after the collision. I think that's perfectly good spot right there. I'm going to mark something. I'm going to mark that spot there. Reset. All right. Let's. I'm going to go 1 centimeter again. That's good enough for me. All right, 0.1167. So I'm going to do a distance over time, 1 centimeter, which is 0.01, divided by the amount of time that elapsed, which is 0.1167. Hit enter. Oh my gosh. This is a thing of beauty. What is my answer? I'll write it at the very top of my board. You can try it yourself if you wanted. It's distance over time. The distance I put in was 0.01 for 1 centimeter. That's what I just used. The time was 0.1167. And I got 0.085. I have to be honest, though. It's 0.0856. Oh, that hurts. No, it's still 0.085. I'm going to keep it. No, I can't do that. If I round it off to the second or actually, we're talking third decimal. Actually, which we're not even allowed to do, right? It has to be two sig figs. Well, I'm not going to do 2 sig figs. Anyways, it's 0.0856. I'm not going to round because I want to prove to you that it came that close. As our prediction, 0.085. So it didn't need magnets for this beautiful, mathematical modeling structure to work out perfectly and match the real world. It didn't. Again, I'll point out that in the first one that you had done with the dart and the car, well, like that was a messy experiment, right? You had a solid collision. You probably had a lot of vibration. You had the dart physically lift the car on the back end, and then it slam back down into the track. There was surely a lot of vibration created from both of those collisions, and that loses energy, and that causes some momentum loss. And so, that didn't give us perfect results. Yet when you look at the magnet one that you last did with the 2 magnets, it was perfect because they didn't have to physically collide. They didn't have to. There was no loss of energy due to vibration or heat or movement of the a sound wave or any of that stuff. That was silent, right? Magnets push off each other silently. It was beautiful, right? Turns out, even in this case, with no magnets, just a piece of putty here. But also pointing out, how much sound do you think this made if this is putty? None, right? It's putty. So it compresses nicely. It doesn't make any sound. I would imagine a very, very small amount. If this putty wasn't here and they just put glue on this and they still stuck together, but you heard a loud crack, these things would have vibrated and this wouldn't have come out as perfect as it did. I would have expected the speed to be a little less than 0.085. But again, it's a thing of beauty. It works out nicely. Again, this is how we do it. This is the modeling that we use. I'm going to make another video again for this is a inelastic collision. I'm going to make another video in a little bit for the elastic collision, similar to lab number 2 that you did. Again, just showing you how the modeling of conservation of momentum looks and how it plays out. All right. Hope you guys find that helpful. And I'll see you soon.